Hi everyone, welcome to Posette conference. I'm Rahila Sayed. I work as a senior software engineer in Microsoft. Today I will be talking to you about monitoring in Postgres and also will be explaining a design of monitoring feature in Postgres. This talk will be useful for developers and administrators who are looking to learn more about monitoring in Postgres. Hi, so let's get started. Let's look into monitoring in Postgres SQL. Let's look at the agenda. First, we'll start by describing monitoring types of monitoring features in Postgres. Followed by that, I will explain a bit about memory contexts and DSAs and DSMs. After that, we'll look into the design of a specific monitoring feature. So, what are cumulative statistics? Cumulative statistics is a subsystem in Postgres which allows you to collect and report information about the server. In this, each process that's doing any activity publishes the counters and statistics into its local memory, it copies it into its local memory, and at a point in time when it is idle, it goes ahead and copies the counters and statistics to the shared memory. Once these statistics are copied into the shared memory, a client which is trying to access these statistics can read the statistics from shared memory and display. Such a client usually calls a function or a view using an SQL command to monitor these statistics. These functions are prefixed with pg underscore stat. The examples are listed on the screen. Pg stat all tables. This is a view that gives you information about accesses to the tables, how many times a table has been inserted, deleted, updated. pgstat-wall gives you information about wall activity, and there are many more like these. These statistics are stored into a file after a server is shut down, except in the case of a crash, in which case it is not saved into the file. So when a server starts up, it can read from the file and it does not have to start from the scratch. The statistics which are fixed size, for instance, wall writer statistics or checkpointer statistics, are stored in the fixed shared memory. While the statistics that are variable, for instance, the number of tables can vary in a particular server. So these kind of statistics, table statistics, are stored in dynamic shared memory. Now let's look at what are dynamic statistics. Dynamic statistics are point in time statistics. They give the current real time view of what the server is doing. For instance, PG stat activity gives you an idea about which transaction is being run by a Postgres process or a backend. PG stat progress vacuum tells you how far your vacuum has progressed. All these counters are updated instantly in the shared memory if the GUC track activities is set on. These statistics are stored in a structure called PG backend status in shared memory. So now let's look at the components of a monitoring feature. The first one would be a monitoring function. This is essentially an SQL function which is backed by a C implementation, usually in Postgres, which is responsible for querying the server for statistics. This can also be turned into a view for more concise output. The next component is shared memory structure to store the statistics. So this can be either main shared memory, which is fixed size, or dynamic shared memory, which can be variable size. The third component here would be Postgres process, which updates the statistics counters. So any Postgres process that is doing any activity updates the statistics counters either periodically and at a point when it is idle, it goes ahead and updates the counters to the shared memory, or it can do it instantly, as in case of dynamic statistics, or there can be a third way to upload these statistics that would be on demand. Like whenever a process is queried for stats, then only it will upload its statistics in the shared memory. The fourth component here is synchronization between processes. So when there are multiple processes trying to access the shared memory, we use LW locks or spin locks to guarantee mutual exclusion of the memory being accessed. The other type of synchronization is signaling between the processes. So we use latches or condition variables to signal between these processes. So now let's dive into a specific monitoring feature, which is memory context monitoring. And for that, let's first look into what memory contexts are. So memory contexts are a way to group memory allocation in PostgreSQL. We group these allocations so that they can be deleted all at once. So it becomes managing memory easier. These memory contexts are arranged in a hierarchy. A memory context can have n number of children, and it is usually a child of another memory context. These memory contexts can be created on the fly by backend. Whenever it's trying to allocate memory, the backend will first create a memory context, and that allocation will then be associated with the memory context. Each memory context is organized in a tree-like structure. When a parent context is deleted or reset, all the children are also deleted. This makes reclaiming memory easier. If you imagine like a tree-like structure, the root of this tree will be the top memory context. And this top memory context is created at the server start. The top memory context essentially is never deleted. It only is deleted when the server stops. And allocating a memory in a top memory context means that essentially you're doing a malloc. So the levels of this memory context trees are numbered starting 1. So the top memory context is at level 1. This is this is something that is used in the monitoring of these contexts. So in the monitoring of the context, the level 1 is the top memory context, and then we go further down. Each of these memory contexts contain the stats about their own memory consumption. Like it will store how many bytes of memory has been allocated, how many bytes of memory is freed. All of that information is contained in these statistics, in these contexts. So when these memory context stats are displayed, it gives you a good picture of the memory consumption of a process. So why there is a need of memory context monitoring feature? There already exist a couple of features that allow you to monitor memory used by these contexts. They essentially list down all these memory contexts and the stats associated with them. The first one here on the screen, which is PG get backend memory context, it allows you to get the memory consumption information, which you can get by querying memory context statistics for a local backend. So it can't query the stats for any other process, and thus it is restricted to only the client backends. The second one is PG log backend memory context. This one essentially allows you to log the memory context statistics in your server logs. The disadvantage of this one is that you have to have an access to the server logs to be able to read these files. And also, the server logs need to be scanned for relevant information, because server logs can have all the other forms of logs and error messages. So you have to scan through the logs to get the relevant memory context stats information. So hence there's a need to have a function which will allow you to instantly query the statistics from any process, not just the local backend, and show it to you on the console, on the PSQL console you're using to query the stats. Let's look at the components used in designing such a monitoring function. The first component is dynamic shared memory, which is DSM. Since I mentioned that a backend can create any number of memory contexts, we need a memory that can expand. The main shared memory in Postgres is a fixed size chunk which is created at the start of the server, and it can't be expanded. So we need something like a dynamic shared memory, which is a framework that creates, manages, and shares memory segments between the two processes. You can do that at runtime when a server has already started, and it is used in features like parallel query and for other IPC needs. DSMs. So this is more about the APIs used in the DSMs. Essentially, if two coordinating backends want to share information between themselves, what they can do is one of the backend can go ahead and create a DSM segment using DSM underscore create. This will allocate memory for the DSM segment, and it will also map that DSM segment to processes local memory. The DSM underscore create returns a descriptor, which can then be passed to the DSM segment handle to obtain a handle to the DSM segment. This handle can be shared between the processes trying to share information. So when this handle is shared by another process, it can attach to that DSM segment using DSM underscore attach and pass in the handle. This results in mapping this segment to any process's local address space. Once a segment is mapped to the address space, one can use APIs like DSM segment address to get to the actual local pointer for that DSM segment. Once you've converted the pointer into a local pointer, then you can access this DSM segment for writing and reading of information. DSM underscore detach is used to detach from the segment, and once all the backends and all the processes have detached, a segment is destroyed. Now let's look at the something called a DSA. It is nothing but an abstraction on the top of the DSM. It handles creating, attaching, and detaching to DSM segments internally, and it provides an interface for the user to create smaller objects and pointers within the DSM segment memory chunk. These pointers are pseudo pointers, unlike regular heap. They are not real pointers, and they can be converted back to backend local pointers. Once a backend has the pseudo pointer, it can convert it to a local pointer to be able to actually access the memory. Let's look at a few DSA APIs. Here we have DSA create, DSA get handle, DSA attach, DSA pin. So DSA create is used to create the DSA segment. DSA get handle is used to get the handle to the DSA area, which can be shared between the backends. DSA attach is used by a process to attach to a particular DSA and then eventually start sharing. DSA pin is used to keep the DSA alive even if all the backends have detached from it. Here I'm using the term backends and processes interchangeably. DSA pin mapping This is used to keep the mapping of the DSA into the local process until the end of the session, until the process is exited. DSA underscore allocate is used to allocate smaller chunks of memory, smaller data types, and smaller objects within the larger DSM segments. DSA free is used to free the memory which is allocated previously so that it can be reused. DSA underscore unpin is used when we want to destroy the DSA after all the backends have detached from it. So now let's look at such a monitoring function. This monitoring function essentially, when it wants to query memory consumption of a particular process, it will send a signal to that process and it will wait for the response from that process after it has published the stats. Then it goes ahead and reads those stats and gives the output to the user. This monitoring function is an a SQL function with a C interface. It, it is implemented. These are some of the implementation details which you see. We add an entry for the function in pg underscore proc.dat, and we include that header in the implementation file where the C definition exists. Okay. So now let's look at the shared memory structure of such a monitoring function. If you see on the left, there is a static shared memory which contains an array of structures. These structures are all indexed by a proc number, and the max size of this array is the max number of processes that you can start in Postgres. Each of these array elements contain a process specific variables. It contains metadata about the actual stats which we store in the dynamic shared memory. It contains LW logs, condition variables. So LW logs can be used to govern access to the shared memory, the DSA stats. The condition variable can be used by a process to signal all the clients that are waiting for the memory to be copied by a particular process. It also contains a DSA pointer. This DSA pointer is basically something that points to the dynamic shared memory area and the memory allocated in that area for this particular process. And this memory actually contains the statistics dumped by this process. And these can be variable sized. Now let's look at the overall architecture. So here, essentially, these are on-demand statistics. A client backend which is wanting to query memory consumption statistics of a process sends a signal to that process. That process then handles the signal in the form of an interrupt handler. The interrupt handler actually goes ahead and sets a bit in the process, which is a global flag. This tells the process that this signal needs to be processed at some point when it is safe to do it. So then the processing of the interrupt happens whenever it is safe in the process to call the processing logic. The processing logic essentially just copies the statistics to shared memory. After copying the statistics, it signals on the condition variable for that particular process to wake up the client which is waiting for the statistics. The client is woken up, and then the client goes ahead and reads the latest statistics. As explained earlier, the synchronization happens using LW logs and condition variables. LW logs are acquired before reading or writing such statistics to the dynamic shared memory. PostgreSQL client waits on the queried process's condition variable to receive the latest statistics. And the same condition variable is signaled by the publishing process when it's done publishing the statistics. So let's briefly look into why dynamic and not static shared memory. So dynamic shared memory is expandable. It can be allocated while the server is running. And also, if we use dynamic shared memory, we can have a dedicated space for each process without pre-allocating large chunks of memory, which we would have had to do in case of static shared memory. um, Static shared memory is fixed size and it is allocated at the server start. So that's why we need to know the size in advance, which is not possible in case of memory contexts stats. If you imagine something like a fixed size chunk, like a queue, for instance, which would have a fixed size, then when the queue becomes full, a publishing process will have to wait for the client to read the stats before publishing new stats. So that would result in wait times and delays at the publishing process. So let's see why DSM versus DSA and which one was used in this particular feature. Since the DSA supports allocation of smaller objects and different data types, DSAs was used instead of raw chunk of memory that DSM provides. It provides flexibility to free the memory whenever it's not used. Let's look into file handling versus aggregate aggregating statistics. So essentially, as I explained, the memory context can grow to a very large value, and we can't store everything, all the context in a RAM. Probably we don't want to use so much of RAM for this particular feature. So we need to limit the memory footprint of this feature, and all the statistics that don't fit in this limit are to be probably saved into a file. But one disadvantage of using a file is that it adds to the overhead of file management. So what we've done in the feature is we have summed up all the remaining statistics and displayed it as a cumulative total. So whatever exceeds the limit is displayed as a single line in the output, which is the total consumption. Now let's look at the API. The name of the function is pg_get_process_memory_context. It takes as an input the PID of the process for which the memory has to be queried. Get summary gives you the summary of the output, in the sense that it does not display the context statistics of all the context, but only the context at level 1 and level 2. And all the contexts which are further down, further below level 2, are all summed up in the level 2 output. Timeout. So this is the number of seconds to wait for updated statistics. And if the updated statistics are not available in these many seconds, then either display old statistics or just display null if old statistics are not available. Let's look at the output of such a function. What you can see is the listing of all the memory contexts by name. These memory contexts are traversed in a breadth first search manner. You can see various columns which are total bytes, which is total bytes allocated for this particular context. Total n blocks means the number of blocks corresponding to the total bytes. Free bytes are the bytes which are free, and free chunks are the chunks corresponding to the free bytes. Number of aggregate contexts tells you the number of contexts that are aggregated to get this particular line of output. So if the get summary is false, what we do is we display each context individually. So number of aggregate contexts will always be 1 for get summary equal to false. You can see here the get summary, the second argument was true. So the number of aggregate contexts for cache memory context is 98. So this particular output contains the consumption for about 98 contexts, including the cache memory contexts. This one is to demonstrate a particular column called path. Basically, the path column can give you the paths to that particular context in the tree. Each memory context are labeled in the breadth first search manner, are numbered in the breadth first search manner, 1, 2, 3, 4, and the path denotes the context's path starting from the top memory context to this particular context. So you can see the context at level 2 will have 2 entries in the path, and the context at level 3 will have 3 entries in the path. This is a customized output which tells you how many total bytes have been occupied by a particular context and all the children under that context. Thank you.